Welcome to today's lesson. Today we're gonna be solving polynomial equations, and we'll do one problem from each section on the homework. So let's start with problem 1b. The instructions say find the zeros. So when we talk about the zeros, we need to understand what zeros is referring to. Zeros is the same as the roots, the solutions, or the x-intercepts. These are all interchangeable in terms of this problem. If I say find the zeros, I'm asking for the roots, I'm asking for the solutions. So recall, when I ask you for the solutions or when I say solve, remember what we're basically doing is setting f of x equal to 0, and then we're finding the x values. So if we set f of x equal to 0, so mind you, we're not setting x equal to 0. We're setting this entire function equal to 0, and then solving for x. So in this case, if three things are multiplied together to give me 0, then by the zero product property, I know that 3x minus 1 can equal 0. The x plus 3 can equal 0, or the x minus 2 can equal 0. If any of these is true, then the expression holds. Then the entire expression will equal 0. So we just have to solve for x. We'll add 1 to both sides, and then divide by 3. So x can equal 1/3. That is one of my solutions. X equals -3 is a second solution. And from the last factor, I get x equals +2. So in this case, I have 3 solutions, and here they are. Okay, let's jump into the second problem. Okay, this one also says find the zeros. So again, I will be setting this equal to 0 and solving at some point, but unlike the previous problem, this expression is not already in a beautiful factored form. I have to factor it first. So I'm getting ahead of myself with that equals 0. We need to factor f of x first. So in order to factor it, since it's not a quadratic, I can't use magic x. I can't use my old methods. Since it's a higher degree polynomial, we're going to use the rational roots theorem, and then test those roots with synthetic division until we find a factor. So this is when we use our p's and our q's. So I'm going to take all the factors of 48, put those on the top. I'm going to then take all the factors of my leading coefficient, which is 1, put those on the bottom, and this will give me my possible roots to start testing. So possible rational roots are plus or minus. So the numbers that go into 48 are, let's see, 1, 2, 3, 4, 6, 8, and so on. I'm just going to start with these because I have a feeling that something will work out and that I won't need to try positive and -1, positive and -2, positive and -3. I have a feeling that we'll work it out before we get to the 16s and the 24s and the 48s. So these are my possible rational roots, and again, it's the combination of every numerator with every denominator. Since I only have one denominator here, my possible rational roots are simply plus or minus 1, plus or minus 2, because it's like 1 over 1, and then 2 over 1, which is 2, and then 3 over 1, which is 3, plus or minus 4, 6, 8, 12, 24, and 48. Oh, and I missed 16. 3 times 16 is 48. Okay, so we found our possible rational roots, and now we have to test them with synthetic division. So I'm going to start with 1. I'm going to test 1. See if it's a root. So if it is a root, that means that I'll get 0 as my remainder. And if that's the case, then what I have just realized is that x minus 1 is a factor. Okay, so having 1 as our test value means that x minus 1 would be the factor that we found out evenly goes in because it had a remainder of 0. But I'm kind of giving you a preview, but let's see if 1 actually works. Okay, I need my coefficients from my original polynomial. So that's going to be 1. Ooh, I'm missing an x squared, if you notice. So that'll be 0x squared. We have to have that placeholder in order to get the right answer. And negative 48. So, bringing down the 1. 1 times 1 is 1. 1 times 1 again is 1. That gives me negative 27. So this did not work. What did we just discover? X minus 1, the factor that this root comes from, is not a factor. It didn't divide in evenly. So we'll try another test value. Now we'll do negative 1. I'm going to zoom through this one a little faster. Again, this didn't work out. Our remainder was not 0. So we just discovered x plus 1, also not a factor. Okay, so now we try the next one. Let's try a positive 2. Bring down the 1. 2 times 2. And now negative 24 times 2 is negative 48. Did I make a mistake? Possibly. Bring down the 1. 1 times 2 is 2. Negative 24. No, looks like we did it right, but we still haven't gotten the answer that we're looking for. Let's try it once more, this time with negative 2. Bring down the 1. 1 times negative 2 is negative 2. 0 and negative 2 make a negative 2. Negative 2 times negative 2 is 4. Negative 28 plus 4 is negative 24. And then negative 24 times negative 2 is positive 48. When I combine these like terms, I do get a remainder of 0, which is a very good thing, because this means that I found a factor, and that factor is x plus 2. So when I divided by x plus 2, using negative 2 in the box, getting a remainder of 0, I learned that x plus 2 is a factor because it divides evenly. So that means that, therefore, f of x is really equal to x plus 2 times this reduced polynomial here, the answer. We have to drop our powers, and now we'll write it in. Great. So we're on our way to solving this. But we have to factor it all the way, and I can still factor this trinomial over here. So I'm going to go ahead and use magic x. The two numbers that are going to multiply for me to negative 24 and add to negative 2 will be negative 6 and 4. So my fully factored polynomial retains our original factor, the x plus 2, but then this trinomial here splits into x minus 6 and x plus 4. Now, finally, we have a problem that looks more like the one that we started with. It's in fully factored form. Therefore, I may set it equal to 0 and solve. So that means x is going to equal negative 2, positive 6, and negative 4. All right, problem 3a. For some reason, forgot to write it down. So it's x to the 4th minus x squared equals 0. Okay, so this guy's already set equal to 0, so I just need to solve this. I need to factor it in order to solve it. So you may think about using the constant term, which is 0 in this case. Well, first there's a lot of missing terms, so we could rewrite it like this. And then do our p's and q's, which would be like 0 over 1. In this case, that's not the best way to go about this problem. It's a little funky. But think back to our factoring methods. Whenever we say factor, no matter how many terms there are, the very first thing that we always check is there a greatest common factor that I can pull out of every term? In this case, x to the fourth and x squared do have a common factor. What multiplies evenly into both? What can I pull out? It would be an x squared. Now, if I factor out an x squared, then the question is, well, what remains inside these parentheses? Well, since I have two terms here, I must have two terms here. And x squared times x squared will give me the x to the fourth. And then x squared times negative 1 will give me the minus x squared that I need. So I can factor it further by looking inside right here and recognizing that that's actually a difference of squares. So I'm going to finish factoring using difference of squares, and now I'm in fully factored form. I'm ready to set each factor independently equal to 0 and to solve. So for this original one, if x squared equals 0, well, if I take square roots on both sides, then x will equal 0. In this case, I'll add 1 to both sides, and x will equal 1. And for the last factor, I get a solution of negative 1. So our final answer is 0, 1, negative 1. These are my zeros, also known as my solutions, also known as my roots. And we'll see tomorrow also our x-intercepts. All right, final problem. So for number 4, you'll notice a bunch of these expressions have numbers on both sides of the equal sign. So before we do anything at all, we need to move all terms to the same side. And we'll do that by addition or subtraction. So in this case, I'll just move the 6x to the other side by subtracting it. And now this is a really common point of confusion. I am just canceling this from the right side. I'm joining negative 6x on the left, but it has no like terms to join with. So I'm not going to do 6 minus 6. I'm not combining these two at all. I'm simply rewriting them separately, since there are no like terms. That's super important. Keep them separate if there's no like terms. Okay, now, I'm missing a term. I'm missing that constant term, which is the 0. And again, when we're missing a constant term, probably not a good idea to do our plus or minus p's and q's. It means that there's a better way. And if there is no constant term, that, by definition, means that there is an x in every term. So we should go ahead and do greatest common factor. So let's factor out the x. We're left with x squared plus 6x minus 6 equal to 0. Oh, you know what? I copied down this problem wrong. Okay, let me redo this problem really quick. X cubed plus, it's just x squared equals 6x. Okay, this is a better problem because it actually factors all the way. Let me try this again. Sorry. Okay. So we're going to bring everything to the same side, as mentioned before. Again, that 6x doesn't combine with anything. There are no like terms. And then we realize that we can use greatest common factor by pulling out an x from every term. When we do that, we're left with x squared plus x minus 6 equal to 0. We have to factor this all the way before we can start finding our roots. So observe here, we can do magic x with that guy. We need two numbers that multiply to negative 6 and add up to positive 1. Perhaps 3 and negative 2. So I'm going to finish factoring this as x on the outside, don't forget about it, and then x plus 3 x minus 2 equal to 0. So our final answer is x equals 0, -3, and +2. I hope that was helpful. Good luck with the rest of your homework.